because we worked so hard to design a reliable power system, but we are destroying it.
AC current.
AC current is very good. AC current is very bad. You don't know. You are concerned about your supply voltage and current. Are you?
Power quality.
Power quality is a very big branch. They will hold on for a strike. They will not allow you to do. They will close your company, right? Why? What is happening to the AC current? Power factor current. Yeah, that's correct. But what do you think is happening to this current? Okay. Let's only talk from the point of basics. You know, positive cycle, 2 diodes turn on. Negative cycles, the other 2 diodes turn on. Okay. Now, when will these diodes turn on? What is the condition for a diode to turn on? You have a diode. I want you to turn on. What will you do?
Threshold.
Threshold, right? Zero crossing or threshold. Let's assume I am ideal diode. So, if your voltage, that is the anode potential, is greater than cathode potential by, let's say, 0.7 or whatever, the diode turns on, correct? What if that doesn't happen? Diodes are not off, diodes are not on. When diodes are not on, there will be no supply current being drawn. Is that correct? This is what happens here. Can you see here? This point is a very crucial point. See, this envelope that you see is same as your supply voltage, correct? But just take a mod. So let's look at this point where your supply voltage is. Your capacitor first charges, correct? And then what happens? Your capacitor is charged to the maximum, correct? Your input is slowly increasing, right? Your input is increasing, and that's how the input increases. And then your capacitor charges. After that, what happens? Your input decreases, right? But your capacitor holds the peak value, correct? So your cathode potential is more than anode potential. Am I right? So will the diodes turn on? No, the entire cycle here, the diodes doesn't turn on. And then it again turns on where your capacitor voltage is equal to your input voltage. And then when the input supersedes your capacitor, it turns on. So this is a conversation between your supply and your capacitor, and your diode is the mediator. You have a common friend. So only when two friends have fight, this guy corrects the mismatch. Otherwise, this guy has no problem. So now what happens because of this? You don't draw continuous current from your supply. Is that right? Okay. Now see, that's how this current looks like. Can you see? This is the supply voltage. Can you see here? This is how this current looks like. It draws some current in the positive half cycle and some current in the negative half cycle. But do you expect this? You want a sinusoidal current, right? Right? So what is happening is something like this. Is that clear? Now, if I try, I don't have, okay, I think I will just increase the size of this so that you. Yeah, can you see this properly? Don't mind if I. Okay. Now, what you see is we did this experiment at IIT Bombay. No, this is not at IIT Bombay. This I did it at home. Sorry. The load was demanding 63 watts of power, but the VA requirement was 120. It's double. Right? This is not just any simulation experiment. You can see 67.037 watt, and then 120 VA was required. So power factor is close to 0.5, right? That you can see here. The power factor is 0.5. Got it? But there's one question I see. Let's see if you can answer this. Power factor is defined for sinusoidal quantities, right? Easily. I have a non-sinusoidal quantity. So when I say power factor, I am talking about the fundamental component of this, right? And there is fundamental, there are other components of it. So you have something called okay. What I mean is I'm also considering the harmonics that are present here, not just the direct direct power factor between this and this. Is that clear? So the power factor is as low as 0.5217. So that means to feed 60 watts of load, right? If you look at the previous slide, okay, the same slide, right? Okay, if you look at the charger is 65 watts. It's drawing 65 watts, but the VA that you're supplying is 120. Is that clear? Okay. Now this is one of the problems. So you can also see the THD. THD is 162%. What should your THD be? 5% or less. So then it's drawing 162%, and you know such chargers are in markets. This is what is a commercially available charger. Okay, but the rating is low. Okay, so you don't see too much of effects on the distribution transformer or somewhere. But imagine an electric vehicle draws something like this, and an electric vehicle is 3 kilowatt. Is that clear? This is one of the problems. Now to do this, let's forget it here. Now to mitigate this, what is the culprit now in the entire converter that you saw? What made the power factor bad? Capacitor. So what is this? Is the best simple thing, remove the capacitor. But you remove capacitor, you see ripples. So what I do is, what is the frequency of the ripple? Double the line frequency, 100 Hertz. Note this. This is a 50 Hertz, so the frequency of this ripple is 100 Hertz. So this 100 Hertz, so you have to remove the capacitor. Now, but if you remove this 100 Hertz, travels everywhere in the power converter. It gets transmitted to any converter. Is that clear? Now what happens? This 100 Hertz component that you see is something like this, right? This 100 Hertz component, you have to give it to your power converter now. Could be a buck or a boost converter, whatever. You should give this. You have no choice, you have removed the capacitor. The moment you add a capacitor of power factor correction, people are not happy. You should remove. But when you remove this, power electronics people go to strike because they have a huge problem. Okay? But in the win-win battle between, power electronics and power systems, power electronics guys have to lose because something can be done. Okay? They are under cost. So now it comes to you. Right? The power system people are happy that somehow you've removed the capacitor, power quality is going to be good, but you don't have a reliable voltage. Am I making sense to you? Check. Now, this is a 100 Hertz ripple, right? What you want is a clean voltage like this. Your 100 Hertz ripple. D is equal to D naught by Dg. You got this point? Why was I talking about this? All this why? It's not to tell you more about power factor correction. It's to tell you this Vg is notorious. I'll show you now what happens. Right? This is a power factor corrected circuit. Okay? I have, I think there's one more PPT which we presented to IEEE Bangalore section. Yes, you can see all of this. We have done some work on this. Can you see? We have corrected. This is without power factor correction. Okay? It draws whenever it wants, whenever the capacitor wants. And then this is power factor correction. We have done this, but okay, we have done this out of a lot of experimentations, and we have done some experimentations on all of this. I also have a video, maybe at the end I will show you the video about it. But you see the output voltage? This is the output voltage. Okay? Even after doing a lot of control system designs and all of that, is the output ripple free? Do you see ripples here? Yes. So you can, these ripples are these 100 Hertz ripples. What I could do, I tell you. I have the sine wave. You can see, right? Okay. The rectifier gave me this. And then I did a lot of mathematics and control systems, but finally I could only do like this. What was expected out of me is this. I could not remove this 100 Hertz. Can you see? That's a 100 Hertz component. I could not do it. Such notorious is this variations in VG. Always remember, if your customer comes up with a requirement that VG is such that he's going to tell you how VG is. He has to tell you how VG is. If he tells you VG is if he tells the frequency of VG to be very high, let's say VG has VG is like this, actual VG is like this, but then he says there are ripples over it, and whenever there is a ripple, I don't want to see my output voltage. But next question you will ask him, okay, that's the case, I can do something, but tell me what is the frequency. And then if he says that the frequency of my ripple is 100 Hz or less than that, then you are in a problem. You are in a grave problem. You have to be a master in designing controller. But if he says instead of 100, it is 100K, then you don't have to bother. Your filter will anyway take it. Right? So such notorious is this VG. Why am I telling you this? Whenever we interview control experts, people with experience who come to us for the jobs, and then when we ask them a question, they are not aware of the problems that is associated with the input, because most of the time the input is taken for granted. Please never do this. Is that clear? Okay. See, I could have skipped this slide in just 1 or 2 seconds, but then more than the control design, I want you to understand the constraints with which we work. Most of the people think control systems people are magicians. They can control anything. No, it is not possible. We are governed by laws of physics, and within that only you can do something. Is that clear? But we have an analytical reasoning as to why some things work and some things don't work. Okay. Okay. So with that, it's 1 hour. It's good time. So almost 1 hour went in only laying the foundation as to what controls are, what control design is, with what constraints we work. Let's go to the problem. Negative feedback and design the negative feedback system. Okay. Now, so the same equation is put up in a block diagram mode. There's nothing there. So the idea is that variations in VG or variations in load, I am supposed to adjust my duty cycle to control the output. Is that clear? Okay. The first question, let's start from here. This is our power converter, right? Or the switching converter or anything. So what you do is, we know what input we want, right? We know what input we want. We know what output we want. This is the expected output. So let's say 13.3 volts. Let's say for a battery charging application, or let's say for ECUs, to power your ECUs in your electric vehicles, you need 13.3 volts as a reference. So that is the reference. And then you match it with the actual voltage. Now what you see is a sensor gain. So in electric vehicles, you see a lot of sensors, right? So what is it? Could be a mechanical sensor, it could be an electronic sensor, it could be anything. Now this sensor is basically to sense this voltage and attenuate its value and give it to a microcontroller, because most of this control developments happen in a MCU, microcontroller units, which can maximum, the ADC pins of your microcontroller can only take 3.3 volts. So what I am talking is 13.3 volts. So I want to convert it to 3.3. So can someone tell me what should be the gain of the sensor? 13.3 to 3.3. What should be the gain ratio? I have 13.3 volts. When I have 13.3 volts, I want to microcontroller. This is in the microcontroller. It should read as 3.3. What should be the gain? No, just the ratio is 3.3 by 13.3, right? Simple. So whenever you have 13.3 cancels, and you get 3.3. Since this sensor gain is for now only that much. It's just a number. But coming to practical EV designs, this sensor is much more than that. Maybe if time permits, I will discuss a little more on sensors. Why am I stressing on all of this is for people who are looking for careers in power electronics. Because I see some BG students are here, right? How many of you are from BG? All BG. So if you're looking at your career in power electronics, all of these matter. they want you to understand the problems, and or let's say perhaps in the first stage, how do you design this, what are the problems associated with these sensors. So for now, let's assume that this is some constant h. It's written as h of s, okay. It matters a lot to us if it's an h or an h of s. H of s means it is much more than h. It is not just constant. It's a function of frequency. That means its output depends on the frequency of input. That's correct, right? H of s. G of s is, let's say if I write it as g of s as 1 by s plus 3, Laplace transform, 1 by s plus 3. What does it mean physically? That means, look, what I am going to give as an output depends on what frequency you give, not just the amplitude. If you're feeding me a very high if you're feeding me an amplitude with a very high frequency, I'm not going to give you what you desire. I'm going to attenuate. That's what it says. So h of s is, that means its output depends not on the amplitude but also on the frequency of what is present there. But let's not complicate too much. This complication comes in practical designs, but this actually makes the design worse. But for now, let's assume this is constant. That is, you have 13.3, you want 3.3. So this is 3.3 by 13. Simple as that. Now this is measured, okay, with the voltage that you want, and that is given to the compensator. Now what this compensator does is this is the device. This is going to tell you what should be this duty cycle. So this calculation is in a way done by this guy. Is that clear? So this person is supposed to look after this, but I don't input this equation as it is. I don't do this. Okay, I don't do it. But this compensator has to understand this error. Look at the error, because one minus the other is the error. Look at the error and tell, look, this should be the duty cycle. That's what this guy does. Is that clear? Layman's understanding? Okay? And this is the duty cycle. Forget about pulse width modulator and transistor, gate driver, all that. So this is converted into duty cycle. Is that clear? So this basically the same equation is taken here. But what is important is, this guy tells you what is the duty cycle requirement without looking at the input voltage. Do we have any feedback from the input voltage here? No, we don't have. So this guy is supposed to understand that. You got it? So this person, without the feedback of your input voltage, right? Without having any contact with VG, should understand that look, there is a variation in VG and update my duty cycle. So this guy has to be very intelligent. So this information this guy should have. And how do the entire control system design is based on this. Any variations in VG, any variations in IO, this guy has to understand without directly contacting them, but he should still have an idea of what is happening there. The moment there are any problems here, this guy is going to update the duty cycle and send it to the converter. Is that clear? He's a manager. Right? The job is to set up this entire lab with a very good manager. The entire job is to design this compensator GC of S. Okay? The same thing is being translated here. The entire power converter is modeled like this. Clear? Clear the definition is? What is that we do when we talk of control designs? Any doubts here? If you understand these slides, then the hands-on is very easy. We just translate it into the form of mathematics. Okay. So how much time do we have?
You can go up to 5.
No, but we have hands-on.
Answer it will be 4:30.
4:30. We have 1 hour of time. One tea break of 10 minutes.
You can take 1 more hour.
1 more hour. That's good. Okay. I think I can manage. You just let me know, sir, when there is a tea break. 1 hour from now, right? Am I going too fast? You could understand, right? Okay. Now, all of a sudden we have changed the topic to small signal model. Okay. The point is to connect to the small signal model now. So this is one of the yet another crucial task that we deal with. Now, to understand what is small signal model, almost all of you are electrical engineers. You have done small signal modeling, have you? You haven't done small signal modeling? Remember? Analog electronics. The first device that you look at is diode. Okay? Small signal model. Small signal model of MOS. Transistors. You have done that. Then if you are, I think small signal model you also get in power systems. Do you derive small signal models in transistors?
Small signal stability.
Small signal stability. That's correct. Small signal stability you do in power system stability. Stability anywhere is stability. Doesn't matter. Okay. So we know small signal models. So the question now is, for just next 5 minutes, try understanding what is the small signal model and why should you do this? Is a very important question, and I'll tell you openly. We hardly have 5% engineers in India who can do the small signal modeling. There is a huge market if they know you are a small signal modeling expert or a control expert, especially if you know how to model small signal, then I think they'll kidnap you. Yeah. I literally don't mean that you will be kidnapped. That means there will be a bargain with respect to your CTCs. There will be, not bargaining as an auction, right? So I give you 30 lakh, someone gives me 40 lakh. Right? You will have a tough time where to go, but you don't find such experts. The reason I'll tell you, 95% of the people don't know what is small signal modeling and why should you do it. Doing small signal modeling is a far off matter. It's a mechanical job. But why should you do a small signal modeling is going to be your first question. If you don't know small signal modeling, why should you do it? Then there's no question of recruitment or something. Okay. Now this small signal model, what it says is, the name says it's a small signal model. That is something to do with a very small signal. Got it? Now let's come back to this. Why do we need a small signal model? Okay. We need control systems. The reason is this notorious VG is going to vary, correct? Right? Let's say VG was constant. VG was very good. VG was an obedient son to its parents, and VG was not varying at all. Do you need control systems? No. VG is constant. Give constant duty cycle. There's no control systems, right? But thanks to this VG, because it's feeding a lot of families like mine, because of which I am existing now. So this VG, it has a characteristic, right? What we saw there, this VG, it's slowly varying. You might say, power system people might say, 50 Hz is just 20 milliseconds, it's very fast, we cannot even imagine 20 milliseconds. But for a power electronics engineer, 20 milliseconds is like walking on is like a tortoise walk. Because we deal with frequencies of 480 kilohertz, 1 megahertz. So let's say if you are running at the speed of 1 megahertz, and then you have a friend who is running at 50 hertz, what do you feel? You feel it's like a hare and a tortoise race, right? Correct? But who wins? The tortoise wins. So here, this guy, you have to win over this guy. This is not easy to win. I told you. If you say that my VG is 100 kilohertz, no problem at all. My control system is taking care. But this VG is a very small signal that is riding at very slow frequency. And that's the reason I want to understand how, if I feed this guy to this power converter, this converter, what will happen to this converter? How will this converter react to this VG? That is the question, and that is why I want this small signal model. Is that clear? Is that clear? Why? So someone asks you, why do you need a small signal model? Your answer should be this. So let's take a very famous example to understand this. If you can do this, then rest everything is simple. I say this for every slide, but yeah, you construct complex things out of very simple things, right? Forget about this converter. Let's say this converter is a diode, right? Okay. So let's take up a diode. I feed some DC to this diode. Okay? Whose value is much more than its threshold. Will the diode turn on? Turns on. I'm not bothered about what happens here. Correct? This is the operating point, right? And then the load characteristics where they both match. Sorry. Your load characteristics also should pass through this. Forget about all that, I'm not doing that. Correct? Now what happens when you, if I feed a DC to this diode, okay, how does this diode, if I have to remove this diode, right, this diode is appearing like a short, correct, or maximum 0.7 volt DC, correct. I'm using constant voltage drop model. If you frankly translate, you will get something like this. Right? That's the characteristic of the diode. Go back to analog electronics. That's what you have seen, right? A diode has three models. One is ideal model, constant voltage model, constant voltage with resistance. It's modeled just like this, short, or modeled as 0.7 volt drop, or 0.7 volt with the resistance. You remember this? The same thing is there. So for power electronics engineer, or for someone who is dealing with very high voltage or something, it is just this. The diode turns on, or if I give a voltage like this, the diode turns off. Correct? I just replace them as open and short. Now the problem is not that. Along with this DC, we also have variations in DC, right? In the buck converter, this buck converter that you see, it is not just constant PG, just like this. It has a ripple over it, which is a very slowly varying ripple. It is 100 Hertz. So this is this. And what I am talking is this. Is that clear? I have used Fourier series mentally to put it into DC plus some frequency. Is that clear? Using Fourier series. So my question is here, and then I have a diode. Right? What did you do in analog electronics all this while? You give a small AC riding over this DC, and then you see the something like this, and then you see that when you have this, sorry, you have it here, you see it like this, correct? So you did this diagrams in your analog lab or somewhere, right? So you have an AC, and that AC is being fed to the transfer characteristics, and you get one more sinusoidal response. Is that correct? Is it making sense to you? I mean, like, you're going back to your basics. In your third semester, this figure you should have seen if you've done a course on analog electronics. Am I making sense or not?
Yes.
Okay. So what is happening is, when you feed a small signal along with the DC to the diode does not behave like a short or an open. It does not behave like a short or an open. It behaves differently. And to understand this, okay, what we used to do is, we took the diode equation as Is into e power V by Vt, correct? And then you partially differentiate this with respect to V, sorry, this is I, okay? You partially differentiate this with respect to V, and you remember you got something like 1 by Rd. You remember this? How many of you remember this? You differentiated this equation, and then you got something like 1 by Rd. You got it like Is by actually V or something like that. No, Id by Vt. I by Vt you got. You get something like this, and then you say current is in the numerator, denominator is voltage, so it should be reverse of resistance. And you call this as dynamic resistance. Right? If you differentiate, you will get this. Right? What you get is, if you differentiate, Is is constant, exponent of something is the same, V by Vt into 1 by Vt. Correct? Now this Vt is same here, and this is nothing but your original I. So I by Vt is what you do. So this is a resistance. So what it means is, if you give a supply and a DC and a small signal AC like this diode will now start behaving like a resistance, whose value depends on the DC value and Vt. You understand this difference? If I feed a pure DC to a diode, it behaves like an open or a short. If I feed a small AC signal along with the DC, it does not behave like that. It behaves like a resistor. The same diode behaves like a resistor. So you can use the resistive property of a diode, right? If you can encash it with this example. Or in other sense, tell me, is resistance a linear or a non-linear device?
Sorry,
It's a linear device, very linear. What you get amplified, right? If you look at the equation of an Ohm's law, V equal to I into R, right? What does R do? V by I. You give a linear signals, you get a linear output. Or this resistance is just a attenuator or an amplifier. If you look V as a signal, I as a signal, you don't have a difference between voltage or current. Resistor is just a multiplier, so it's a linear thing. So what did you do? You linearize your diode. What was the characteristic of your diode? The diode was a non-linear device. It's a non-linear. It's e power V by Vt. It's a very non-linear, right? If you have some idea about computer science, there is something called as big O. Have you heard of this big O operator? It's called big O. Big O operator tells you how fast a signal grows. If I have an exponential or a polynomial, big O tells you exponential or polynomial which grows faster. So this is a very non-linear thing. It grows very faster. But what did you do the entire e power V by Vt? You just made it as a resistance. It's a linear thing. You linearized the entire diode. If you can linearize diode, you can linearize anything. As simple as this. So what I do is whenever there is a small signal, a very small amplitude and a frequency is very large, the diode, which is highly nonlinear, behaves like a simple resistor, or in a way it is linearized. Right? So one more example to this is, if you look at purely mathematics, if I ask you whether it's a linear or a non-linear curve, what do you say? Non-linear curve. Then I ask you to only zoom this portion, and then I only show you this portion. Linear or non-linear? Linear. So what are you looking at? You are looking at only this portion of the curve. Your amplitude is very small. You are looking at only this portion of the curve, which is this. Right? This was your sinusoidal wave, and this is what you got. You are looking at a very small portion of the curve, and which means the entire curve is non-linear, but it is piecewise linear, correct? And what we are looking at here is only that portion of the curve. Is that clear? My input is only this much. Within that, I don't have to look at the entire characteristics of the diode. I am just looking at this portion of the curve, which means it's linear. And this is called the small signal model. The signal is small, the frequency is also small, and you don't need to worry about e power V by Vt, entire large view of the curve. You only look at the small view of the curve, and then it is linearized. And this is the basis of linearization. Whenever you say linearization in power systems or power electronics, which means you're looking at a very small portion of what you want, and so small that you can equate it with y equal to mx plus c, which is a linear portion. And that's what we are doing here. Because I don't want too much of the content. I want only the variations or the disturbances that are there, which is a very small signal. The disturbances are characterized as very small signals. So the entire curve, the entire converter that you see here just becomes this. Got it? What is the difference between these two? There is no switch. The switches are all removed, and this becomes any converter that you can solve using any of the circuit solving techniques. If I ask you to calculate what is the output voltage V with respect to Vg, you can apply Thevenin's theorem. You can apply what all? We have many laws, right? Node voltage analysis, mesh analysis, all that you can apply in it. You have a number of techniques to solve. But if I ask you to derive V by Vg, you have a switch which turns on and turns off. You can't just apply circuits, because the subject says it is linear circuit theory. Only applicable if it is linear. This is not linear because there's a diode. Now look at this. There's no diode. Everything is linear. Is that clear? That is the beauty of small signal modeling. If you have the potential to convert any circuit to this, then everything people can take care from here. They don't have to do. But who converts this is a big question. If you do any mistake in this, entire control theory goes into, it just ends in smoke. Is that clear? So this is a very important thing. I am not discussing how did we derive this, but understand the open loop to, understand the, this is called the actuals converter, this is the small signal model. Is that clear? We do derive small signal model because the variations in VG is very small. But whenever there is a small variation, we are into problems. So we want to understand when VG is small, it is varying like this, how my entire converter looks like. So they say, look, when your VG is very small and the frequency is very small, don't have to bother about switching. The entire converter looks just like this. Is that clear? Okay. And then I can easily write expressions. My output voltage is a function of duty cycle. My output voltage is a function of input voltage. My output voltage is a function of load. Clear? And you know transfer functions, right? The very basic of transfer function, there is one assumption that you make. Whenever you derive transfer function, you only consider one input. You don't consider 2 to 3 inputs. It's the ratio of output to input when the other inputs are 0. Is that correct?
Yes.
Do we consider 2, 3 inputs at a time? No. That's not a transfer functionist effect. Why? Because you can only bear one disturbance at a time. You have a disturbance from your wife, you have a disturbance from your son, you have a disturbance from your mother, you just go run away. You can't deal with these 3 disturbances at a time. You have a disturbance from a wife, you can handle her. But when your son or your child and your mother is at peace, there are peace in the world, you can handle. One thing you can handle at a time. Same thing is here. Everything is done by the law of physics. I can only handle disturbance in the duty cycle when these 2 disturbances are 0. I can't give all the disturbances at a time and say, look, controller, you perform wonderfully. Not possible. Got it right? So analysis also does the same thing. So what we do is we derive, look, I want to see what happens to my output when there is a disturbance in duty cycle, provided I don't see disturbance in my input and the load. Next, I want to know what is the influence on the output, what is the output with the VG, variation in VG, when there is no disturbance in the duty cycle and no disturbance in the load. Next, I want to know what happens to output whenever the load changes, provided there is no disturbance coming from input and from the duty cycle. So you only consider one disturbance at a time. These are the most fundamentals of control designs. Your questions will be based on this if you are attending interviews. On what basis do you define a transfer function? You have 3 disturbances. Your answer should be consider only one at a time. Right? So the entire large signal model is translated into a small signal model with these perspectives. And what you see is now, instead of this converter, the big converter that we saw, we replaced it with a very small converter where you can apply linear techniques, linear circuit analysis techniques to derive the further equations. Any doubts still here? So we saw, we have, how much time do we have, sir? Half an hour we have or 15 minutes? Or done? 20 minutes. Good. Okay, sure. We have 20 minutes of time and then we are breaking. Oh, good. Okay. Okay, so what we started with, can someone tell me what's the first point we started with? I would like to connect it together. What is the first point? Yes, sir. From the basics buck converter we saw, the most basic converter is a buck converter and anything can be realized out of a buck converter. We saw how boost can be converted to buck, how inverter can be converted to buck or anything.
We can use 5 minutes breaks.
Now,
Yes.
okay, and then we have how much time after that?
Now it's 3:40. So 3:4:30 if you want.
Okay, so
otherwise you can take to lab.
we'll continue. We'll finish here because the entire setup is done here. And 4:30 we can go to that.
No, oh yes sir. Now we'll have break.
And then they are coming back here only, right? So 10 minutes we can break,
Yes.
and then I'll adjust the entire things for the next 40. So we have 45 minutes or?
Yes, sir, yes, we have some.
Okay, sure. Thanks. So we'll break out. We'll have the recap session after we are back. That will show the efficiency better. Thank you. ಅಲ್ಲ ಇದರಲ್ಲಿ ಒಂದು ಸ್ಲೈಡ್ಸ್ ನಾವು ಅಲ್ಲಿ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಮಾಡ್ತೀವಿ ಇದು ಬೇರೆ ವಾಟ್ ಐ ಕ್ಯಾನ್ ಡೂ 4:30 ಮಾಡಿ ಬಂದೆ ಒಂದು ಸೆಕೆಂಡ್